Hello, today we're going to be talking about feature stores. But first, a quick introduction. I'm Orr, and I'm a software engineer. I lead work on Lemonade's machine learning platform. And Lemonade is a full-stack digital-first insurance company driven by automation and behavioral economics. So let's get started. Machine learning in production is considered difficult, or running machine learning algorithms in production is considered hard. The most popular slide to show this is from a 2015 Google paper titled Hidden Technical Debt in Machine Learning Systems, and this is the most popular diagram from that paper. I'll show this slide as well, since I don't want to deprive anyone of seeing it for the first time. The most famous quote from the paper is, "Only a small fraction of real-world ML systems is composed of the machine learning code, as shown by the small pink box in the middle. This required surrounding infrastructure is vast and complex." So the lighter pink boxes maybe have to do with data, whereas the boxes in white are sort of general for all software, or all software running in the cloud. So this complexity has led to an explosion of machine learning tools and the term ML ops, machine learning operations, with hundreds of companies and open source tools having become available in the past several years. A very large proportion of these tools solve problems with model training and serving, but we're here to talk more about tools that have to do with data. So staying with our definitions, we can roughly divide a machine learning system into data and code. Code is anything having to do with the model architecture, the business logic, glue code in order to make this model run, or train in training, run in production. And data is the features. It's what we feed into the model in order to train it. And in order to make inference in real time. Deployment of code to production is something that's been revolutionized by the DevOps movement in the past decade or decade and a half. And machine learning code is not that different. We may have some specifics like model artifacts, or maybe we need to use GPUs in order to infer, but the basic principles remain the same. We can deploy code to production. Data is a completely different story, as data is dynamic. Testing data can't necessarily be done before production, and there are a bunch of different other challenges, which we'll see soon. But first, let's define our data building block, the feature. So what's a feature? A feature is an individual measurable property. In this talk, we're talking mostly about tabular data, but the definition of a feature remains for data in computer vision, NLP, and anything deep learning. In tabular data, a feature is either raw data, a row-level transformation, or a column-level aggregation. So raw data in our example would be our user date of birth. A row-level transformation would be the user's age. So maybe we would subtract the date of birth from today's date and gain the user age at a time of prediction. And a column-level aggregation would be maybe the average age in a certain cohort or something like that. Often these features will be very refined data, making them very important for data-driven organizations. And a lot of data science effort goes into feature engineering. The number 80% is thrown around a lot. I don't know, you decide for yourself. So what's so hard about data in production? Let's take a look at just a few examples. The first example is skew between training and inference. So for each feature we use to train a model, exists a pipeline to calculate this feature offline for many rows. So we want to create the training data. But then when we decide to make real or near real-time predictions, we also need a separate pipeline to calculate features with low latency, which presents its own challenges. Not only is it challenging to create this near real-time feature pipeline, but they're also separate implementations, and these two separate implementations are bound to introduce skew or differences, or slight differences eventually. So not only is it difficult to create these separate pipelines, but we also have many of them. We may have a pipeline per feature, per model, over different models and different teams in an organization. Organizations have hundreds to thousands to tens of thousands of features running in production, depending on the size of an organization. So data pipelines are also hard to test and monitor, as data is dynamic. We don't necessarily know where to even run these tests. Can we run these tests testing data before in CI, maybe before we enter production. The SLAs we want to guarantee probably say that no, we need to test in production. So maybe we want to guarantee data freshness. We want to know that we have the latest data. We want to know that the distribution doesn't change over time. We want to know that the volume is reasonable to what we expect and that the schema of the data hasn't changed. And of these SLAs, what's even good enough? It may be different for each model or for each situation. And finally, it's not only difficult to deal with the data infrastructure and monitoring and testing, but the actual business logic of the data pipelines themselves may present some challenges. An example of this is point-in-time or time travel data, the ability to create data for training. So let's just look at an example to show this. So let's say we have a users table with several columns and a transactions table also with several columns, and we have many transactions per user. One day a new user is created and added to our users table. Then that user makes a transaction, and that transaction is joined with the users table. And finally, that user changes some of their data. So in this case, the user changed their date of birth from null to a date. Down the line, we decide to make a prediction, an online prediction during the transaction. And we need to recreate this data for training. So the data in the business database has changed. We now see a value in the date of birth instead of null, which was the value during the time of transaction. But we need the values during the time of transaction to train on because we plan to predict at this point in time. So even if we manage to save this data, maybe with change data capture or event sourcing or some other architecture, there are still challenges in a lot of room to make mistakes when trying to materialize this data. So hopefully I've convinced you of some challenges of data in machine learning and production. And the way a lot of companies are solving these challenges is with a new paradigm called the feature store. So what is a feature store? A feature store is a single interface to create, discover, and access features for model training and inference. Basically, a feature store will ingest features from different sources, save them into two separate stores, one low latency and one high throughput, and have APIs, one low latency and one high throughput for training and inference. So our feature store, we want to be able to ingest both from streams and batch jobs. We want to be able to serve low latency single features for inference and high throughput bulk features for training. We want to be able to engineer features, do row level transformations or column level aggregations. And we want to be able to discover features. That's a very important one. So although the word store is in the name, the feature store is not just a storage layer to unify low latency and high throughput persistence. Like we see in the diagram, feature engineering is a very important layer which we want in our feature store. But what do we gain from this paradigm? First and foremost, by dividing ML in production into features or data and models or code, we're decoupling feature engineering from feature usage. This decoupling will allow us to separate work from separate data practitioners and to work in parallel, and for each subsystem to have a single responsibility. Next, we gain training and inference feature unification. If before we were developing the training and inference data pipelines separately, now we develop a single pipeline and the feature store takes care of the rest. But the levels of abstraction are usually higher than just the pipeline that we had before, so now we're just developing a feature. We're writing business logic to make transformations or aggregations and develop features, not pipelines. And what we gain from this is a guarantee for training and inference time feature equality, and an easy development with high-level abstractions. And we'll see how this empowers our data scientists later. Next, we gain the ability to reuse features created by other scientists or other teams, like the reuse of code, but for data and infrastructure and between teams. This will save both precious engineering and computation resources, and will help with the cold start problem of starting a new model. And with a bunch of other things, it's quite obvious why reusing features is good. To facilitate this reuse, we want to discover existing features with an API or SDK. We see an example of that at the bottom. Next, we gain the ability to monitor in a single location. So like we see in the green lines, we can monitor the inputs to the feature store and the outputs. So the challenges we presented before were guaranteeing SLAs of volume, schema, freshness, and distribution. So on the input to the feature store, we can monitor volume, schemas that are inputted from different sources, and freshness. And when requesting features from the feature store, we can monitor distribution of the data. And we can also add maybe miss ratio from our cache, requesting features that don't exist, and latency service level agreements. So how does this empower our data scientists and improve our velocity? So instead of difficult to create feature pipelines, we have easy to create features. So instead of creating pipelines, we're just writing business logic for features. So instead of data scientists building infrastructure or communicating requirements to engineering, now they author features. Instead of consolidated ownership of business logic and other SLAs and infrastructure, data scientists own the business logic and are accountable for feature engineering business logic, whereas other tools or teams are accountable for the freshness of the data and monitoring and other things. And instead of difficulty to discover and use existing features within a team or between teams, the feature store has metadata and it's quite easy to discover features. So hopefully I've convinced you that this is quite useful, and let's look at our options to build, buy, or maybe something in between. First off, let's look at some open source solutions. There are two main ones, Feast and Hopsworks. Feast is more of a standalone feature store, and Hopsworks is more integrated into their full machine learning platform. But the main thing about the open source solutions is that they currently don't provide feature engineering. They really are just the storage layer and the metadata layer. So you have to do your feature engineering before features enter the feature store. So they'll just do training, inference, parity, but not engineering. Feast is quite a bit more popular on GitHub, and they newly support AWS in addition to GCP. So let's look at how an SDK looks for an example open source solution. Basically, we would register a stream. We're registering the Kafka source here from customer transactions, and register an entity, a customer, where the index of the customer is the join key. So we'll request features, single features using the customer ID. Then to get training features, we can request all features with get historical features, feature 1 and feature 2, or all rows. And if we want to get a single row for online inference, we can add the entity row that we want to get. In the example, customer ID 100. So these SDKs allow you to set up the feature store and author features for model training and inference. Next, let's look at some paid solutions. There are a number of paid solutions, several of which are quite popular and others which came up in a Google search for me. They each sort of solve different problems. So the first is AWS. The SageMaker feature store is the same as the open source ones in the terms of functionality, except it's SaaS, so it's very easy to deploy. Tekton, which also as of recently developed Feast and have very similar APIs to Feast now, add the ability to do near real-time transformations and aggregations, which is a big one, so feature engineering. Hopsworks and Ingestion are sort of fully functioning machine learning platforms which help deployment of not only the data, the features, but also the code or the models. And Molecular, which I don't really know, but seems like they may be good at low latency for really big data. So let's look at some requirements from our feature store. The first is governance. So we may want to be GDPR compliant, or we may want to limit the amount of features that some teams can use, or which features are available for which teams. I think all of the paid platforms supply at least some sort of governance. Feature engineering is a big one, and I think it's a very important one because either we do it inside the feature store or we do it before the feature store, and it really pays off to do it in the feature store. So again, only several of the paid solutions do feature engineering. Joins, online or offline joins. Like we saw in our example where we were joining the users table to the transactions table, if we were streaming the data separately, we would need the feature store to be able to join this data both for training and inference time, because maybe we'd get a transaction ID, but we'd want to get data about the user. And so we need the feature store to be able to join this data. And time travel is also a big one for some companies doing online inference, like we saw in the same example I just mentioned. Feature sources, we saw stream and batch sources, but APIs are also a big source for some organizations, whether it be public APIs or internal APIs. And the ability to put features synchronously versus processing them asynchronously is also, I guess, important if you want to manage race conditions in some way. And feature versioning, again, is a nice requirement to have. So there are some things that no vendor or open source solution can provide you. So no one can provide validation that processing of your asynchronous queue will be on time versus your synchronous request for features. So like we said, the feature store in real-time processes, I guess maybe a Kafka topic. And then we synchronously request features, but no one can, or the feature store can't promise that it will process these on time because you may request the features before you actually put them in the queue. So this is something that your business logic needs to validate. The next thing that's quite large is backfill of legacy data. So feature stores start to process data from when you put this, or when you add this queue. But you may have legacy data from different types of formats. Maybe you even have snapshots of databases that you somehow want to enter in the feature stores. And there are APIs to add data, but you still have to curate the data manually that you want to enter. And this is quite a big one. The feature store will allow you, though, to do this once per feature, which is quite nice. And finally, a good software abstraction is very helpful, but it's only one step to healthy data organization and a good relationship between data scientists and engineers. Okay, so your company, if you're quite mature, if you have a mature engineering organization, especially your data platform, you really may be a special snowflake in this case. There's no current standard to develop a feature store. It really depends on what your internal infrastructure needs really are. So the featurestore.org is a great website which compares the internal implementations of a bunch of different companies in feature stores and open source feature stores and proprietary feature stores. And what's great about this website is that there's this table that I'm showing, and you can see that no feature store does something exactly the same. So their offline stores are different data warehouses and different query engines or data lakes, and online stores use different databases, and they some save metadata and some don't save metadata. Twitter's is only a library, it's not even a service. Only some of them support time travel. They use different frameworks to calculate features in different online and offline databases. Some they support training data in different formats. So it really depends on what your organization needs. And the landscape is gaining more and more maturity, but it's still not very mature. So like many of the above organizations, at Lemonade we went with a full-blown internal implementation. When we started developing, the feature store landscape, like I said, was not very mature, and it's still changing very rapidly. There weren't any proprietary solutions to purchase, and open source solutions didn't provide feature engineering, which was our main requirement. We did manage to utilize our internal existing infrastructure and tailored the specific abstractions that we wanted to our exact needs. So there are slight advantages. So what I want to take away is that maybe build is an actual option, or maybe build some is an actual option. So do I need a feature store? I think if any of the above points are answered, are true, then you may want to consider a feature store. If you're doing online inference, then you need to create training data, which is separate for online and offline. And you may want a feature store to unify these pipelines. If you have more than a single data science team and you're finding it difficult to share features between them, then you may want a feature store. And if you have only over a certain amount of features in production, then again, you may be finding it difficult to manage all of this infrastructure, and you may want a feature store to help with these abstractions. That's it. If you think working on machine learning platforms is interesting, my team at Lemonade is hiring. You're welcome to reach out. Lemonade is also hiring for a bunch of other open positions. I'd be happy to answer any questions you may have in just a moment in the conference platform in a breakout room, or either by email or LinkedIn later. Thank you very much for joining.